Hello, everyone. We are happy to welcome you all to this heidelberg.ai event. Before starting, I would like to first thank our sponsors, which are the Department of Medical Image Computing, which is led by Professor Klaus Meyer-Hein, and the Interactive Machine Learning Group of Dr. Paul Jäger. Both of them are of the German Cancer Research Center. And moreover, we're not only sponsored by them, but also by the Helmholtz Imaging Group and also LS Unit Heidelberg. And moreover, we would like to thank our partners of the NCT Data Science Seminar. As always, this talk will be recorded and uploaded on YouTube later. And moreover, the slides of the presentation will also be shared and made available. For our event today, we are very happy to have Professor Pearse Keane with us, who will talk about building foundation models in ophthalmology from a clinician's perspective. Pearse Keane is a professor of artificial medical intelligence at the Institute of Ophthalmology at the University College London, and is a consultant ophthalmologist at the Mooresfield Eye Hospital, London. Since 2020, he has been funded by UK Research and Innovation, UKRI, as a Future Leaders Fellow, and in 2023, he became a National Institute of Health Research, NIHR, Senior Investigator. Since 2016, he led work on developing AI algorithms for early detection and treatment of retinal disease and early warning systems for age-related macular degeneration, with both projects published in Nature Medicine. Most recently, he led the development of RedFound, the first foundation model in ophthalmology, which was also recently published in Nature. Moreover, he was included in the list of the most influential Londoners on the Evening Standard Progress 1000 in October 2019, was profiled in The Economist in June 2020, and was listed in the top 10 of the Power List by the Ophthamologist magazine. Given this impressive track record, we are very happy to welcome him here and have him talk about his latest research projects. So without further ado, I will hand over to Professor Pearse Keane and start this event off. Thank you.
Thank you. Thank you, Tassilo, for that very kind introduction. And one thing that I didn't include, one bit of information that you didn't mention in that introduction is that although I'm based in the UK, I'm actually from Ireland originally. I'm from Dublin, and so it's probably not going to be obvious to anybody on the call, but that's where I'm from originally. And so just to highlight. So while I share my screen, let me just get things organized. So I'm going to talk about building foundation models in ophthalmology, and I'm going to try and give a clinical perspective. And so really the last part of my talk is going to focus on the efforts that we've made to build what's called RedFound, which is retinal foundation. So this is, we think, one of the first foundation models in ophthalmology. However, I'd like to give a broader perspective and tell you about all the work that we've been doing on seeing how you can develop AI systems for healthcare, share any kind of learnings, share any challenges that we faced. And so one of the advantages of my perspective, I think, is that I potentially can cover the full spectrum of AI in healthcare. So going from an idea to an algorithm, and then going from code to clinic. And so having a kind of working knowledge of all those parts, I think is one of the things, one of the perspectives that I can give. Now, on this title slide, I have given my Twitter or my X handle, so I'm always looking to try and get more followers on Twitter. But also on the last slide, I'll also give my email address. And so please do get in touch. And as Tassilo has said, I'm happy for this to be recorded, and I'm happy for my copy of my slides to be shared. But if there's ever any other questions, please do get in touch. So we've already had a little bit about my background. So I'm a consultant ophthalmologist in Moorfields Eye Hospital in London. And so really that's my professional background. I'm a clinician, I'm an ophthalmic surgeon. I specialize in the treatment of retinal disease. And so in particular, like the #1 condition that I know the most about is age-related macular degeneration, or AMD. And AMD is the commonest cause of blindness in the UK, in Germany, in the US, in Europe. You know, it's it's really a major thing, and it's something that's just getting worse and worse as the population gets older. The other condition that I specialize a lot in is diabetic eye disease. And diabetic eye disease is the commonest cause of blindness in people of working age in many countries and regions around the world. And so again, that's also something that's becoming more prevalent as you know, a lot of low and middle income countries are starting to have more resources and people are living longer lives, and that's becoming a bigger issue. Now, the other aspect is that I'm a professor of artificial medical intelligence. And this was a term that I coined myself, actually, just to really describe the fact that I lead a multidisciplinary clinical research group that aims to develop and apply AI in healthcare using ophthalmology as an exemplar. So it's kind of like, you know, we want to try and do things that will cure blindness and prevent blindness and give all these benefits, but we also want to see how we can do cool things or learn new things, generate new knowledge that can be shared with other medical specialties, both clinicians and data scientists and machine learning experts, so that they can do things well. They can do things in other aspects of medicine, whether it's cancer or cardiology or other specialties. The other thing is that I'm funded by UK Research and Innovation. The reason that I came to the UK, so I was originally I was spending a few years in Los Angeles doing my clinical training there, and I came to the UK because of the support that they have for clinical academics. Now, the other thing to say is that these are my financial disclosures. None of them are really directly related to this, but in particular, I think it's worth highlighting that I previously worked as a consultant for DeepMind, and I also act as an advisor for the startup Bitvent, which I'm going to briefly mention in this talk. So, as an ophthalmologist, my whole life really is focused on examining the eye. And one of the things that non-ophthalmologists may not know is that ophthalmology is very specialized now in many respects. And so I'm a retinal specialist. And so I spend my working career trying to ignore the front of the eye and trying to figure out how to look through this keyhole, which is the pupil, to look to the back of the eye. And a lot of the time thinking about how we can take photographs of this dark cave, which is the ocular fundus. Now, since the 1960s, with the advent of electronically timed flashes and high quality 35mm film, we've been able to take good images. And then, you know, that has improved quite a bit over the coming decades. So we can now take images without dilating the pupil for the most part. We've moved from capturing things on film to capturing things digitally. And we even have clip-on lenses that we can put on our smartphones that we can allow us to take images of the ocular fundus that are pretty good. So this is the retina. This is the ocular fundus. This is a photograph, I think, taken of my eye a number of years ago. And this is everything that we look through when we can illuminate that keyhole and look at the back of the eye. So we see the optic nerve and the blood vessels and so on. Now, much of the focus of my research has been on a type of imaging called OCT imaging, or optical coherence tomography. And OCT was first described in a paper in Science in 1991. And interestingly, it was a medical student called David Huang, who was doing his combined MD PhD in the lab of Jin Fujimoto at MIT, who essentially had the idea for how to do this type of imaging, and then happened to be working with this world-leading lab to see how they could put things together and lead to this breakthrough. And so that was back in 1991. And of note, just last year, David Huang and the other inventors of OCT won the Lasker Award. And the Lasker is one of the big predictors of Nobel Prizes. Now, as it happens, the other winner of the Lasker Award last year, in a nice coincidence, was Demis Hassabis and John Jumper from DeepMind. And so it'll be interesting to see, you know, which Nobel Prize comes first. Now, when we talk about OCT, this is a type of tomographic imaging, and we take multiple cross-sectional scans, and then we can generate a three-dimensional view of the retina. And the nice thing about it is that we have a very high axial resolution. So the axial resolution is about 5 or 6 micrometers, so thousandths of a millimeter in resolution. And it gives us these very nice cross-sectional views of the retina. And it gives us a resolution that's an order of magnitude better than a CT scan or an MRI scan. And the cool thing is that it takes just a second or two to take these scans, doesn't involve any radiation, and it's completely safe and easy to do. And so I feel very fortunate that my professional career, both as a clinician and as a researcher, has coincided with the kind of rollout of this technology and all of the ways that it's transformed clinical care. So we now do more OCT scans than all other ophthalmic imaging combined. In fact, I've been so obsessed with OCT scans over the last 2 decades that the Christmas present that my wife gave me last year, I can't resist showing you, but she got me a pair of Vans with an OCT thing on it. And for those other nerds in the audience, it's surprisingly easy to go in with any sort of image file and get it printed on your Vans. So just a tip for others. I'm sure there's some deep learning related things that might be equally cool or equally nerdy. Now, OCT, as I said, has become the dominant imaging modality but that raises a number of problems. So the first problem is, I think, captured in this letter that we wrote to the American Journal of Ophthalmology in 2020 about trends in OCT utilization. And so what we highlighted in this letter was that between 2008 and 2016 at Moorfields Eye Hospital, we've seen about a 14-fold increase in the number of OCTs that we perform. And in fact, since 2017, we've been doing about 1,000 OCT volume scans per day at Moorfields. And since 2022, we have about 20 million ophthalmic images in our data pipeline at Moorfields. So that's not just OCT, but OCT is the predominant imaging modality. So that is a major challenge for us because we need to have human experts that can interpret these scans. But of course, it's potentially also an opportunity because maybe this is the perfect substrate for developing artificial intelligence, machine learning, deep learning solutions, etc. Now, what other problems? Well, another problem, but also an opportunity, is that since 2017, we've seen OCT rolled out in primary care optometry settings all around the UK and in many other countries around the world. So in the UK, if you want to go and get a new pair of glasses, you go to an optometrist in your local town, your local village, and you get your glasses changed. But it's very common now that you will have an OCT scan as part of your test. And so this is an announcement from a number of years ago now about Specsavers, which is the biggest optometry chain in the UK, but has branches all around the world. And essentially, they rolled out OCT scanners, and they do about 9 million OCT scans per year in the United Kingdom, or 9 million eye examinations per year. Now, I think that's overall is a very good thing. And generally, if any relative of mine is getting an eye test done, I think it's a good idea for them to have an OCT scan done. The problem is that this is a little bit like if every family doctor in the country was given their own MRI scanner or their own CAT scanner, and they were able to take it on every patient who came into them with a cough or a headache, and it just took a few seconds to do, and that the expertise in terms of interpreting the scans was very variable. So the problem now is that we get a huge amount of patients being referred into the hospital eye services because of false positive findings or overly cautious referrals. And so that leads to a lot of challenges in the system. Now, the last problem, and probably the biggest reason why I think we need AI in ophthalmology, is that since 2017, ophthalmology has overtaken orthopedics in the National Health Service in the United Kingdom in terms of clinic appointments. So nearly 10% of all hospital clinic appointments in the UK are for eyes, That constitutes just under 10 million visits per year. And that's a number that's increased by more than a third over the last 5 years. And so the brutal truth is that there are some patients that are going blind because of delays in being seen and treated. And this is not just a problem in the UK, it's also a problem in Germany, in Europe, in the US, and many other countries around the world. And this is to say nothing of low and middle income countries. And so what I believe is that new technology and innovation can help, at least in part, to begin to address these things. Now, of course, it's not a panacea, but you know, if we can improve things even by a small percentage, then I think that there's huge potential benefits. Now, I think people like me, you know, ophthalmologists, we often like to claim that ophthalmology is one of the medical specialties at the forefront of AI in healthcare. And I think that's definitely an arguable point, given that radiology perhaps has more like regulatory cleared devices. But the fact of the matter is that the very first autonomous AI system in any medical specialty to receive FDA clearance in the US was for ophthalmology, and that was for diabetic retinopathy screening. And that was in 2018. And then, in fact, the second ever autonomous AI system in any medical specialty to receive FDA clearance was also for diabetic retinopathy. And that was in August 2020 for the company iNuke. And so we're starting to see these systems begin to go from research papers into things that are in clinical practice. Now, we also have an involvement of companies like Google. They developed a system called ARDA for diabetic retinopathy screening. And that system is now being deployed in some low and middle income countries. And so they, in particular, have deployed it in Thailand and in India. And it's been really fascinating to talk to some of my friends and ophthalmology colleagues in Aravind Eye Hospital in India. And I know that they've used the Google system in over 350,000 patients in real life. And so that to me is exciting because it seems like the first signal that we're beginning to move beyond just the hype of these AI systems and the kind of earlier conceptual steps in their development. Now, having said all that, I think it's really important to have a realistic sense of what is the current state of adoption of of clinical AI systems. And so there's a very nice paper that came out in this new journal, the AI journal from the New England Journal of Medicine, and it came out in November of last year. And this is led by James Zhou, who is in Stanford and is one of these people who's really doing a lot of cutting edge medical AI work. But in this paper, it's not so much about a cutting edge AI system, but it's actually just looking at a large billing database in the United States and looking at billing claims. And I thought it might highlight as some key points from the abstract. So the first is that as of last year, there's over 500 medical AI systems that have got US FDA clearance. And they looked at a database of more than 11 billion payment claims between 2018 and 2023. Now, the good thing from an ophthalmology perspective is that the diabetic retinopathy screening tool that I described from 2018 from the company IDX, that was the second most used system. Now, the slightly less positive thing is that only 2 systems out of over 500, only 2 systems out of over 500 actually had more than 10,000 billing claims. And that is in a database of more than 11 billion claims. So I think we just need to be very conscious of the fact that we're still in the earliest days of actual adoption. And you could meet most ophthalmologists in the US and they will never have encountered an AI system. And indeed, most ophthalmologists in Europe and the United Kingdom, etc. Now, my own work in this space really began back in 2015 and 2016, when I guess it even goes back to 2014, when I had been reading about all the advances in deep learning, in computer vision, reading about the ImageNet challenge and the triumph of deep learning in 2012 and so on, and all these kind of historic pivot points in the history of the field. And so I was looking for collaborators, and I remember, going to some university collaborators, and there was only I guess a smaller number of people who were really into deep learning at the time, or at least that I knew about, that were into deep learning. And at the time, I was mainly met with shoulder shrugs, and people weren't really that interested in getting involved. And so I decided to see, could I engage with industry? And so I read about DeepMind, and I read a profile of DeepMind in Wired magazine in July 2015, and I thought, these are the people that I should contact. And so essentially, I sent an email, I sent a message on LinkedIn to Mustafa Suleiman, the co-founder of DeepMind, and I said, I'm an ophthalmologist at Moorfields. We're doing 1,000 OCT scans per day at Moorfields. There are people who are going blind because of delays in being seen and treated. Can we work together to develop a deep learning system to try and address this? And so fast forward a year from then, and we were able to put in place a research collaboration agreement with DeepMind. And initially, back in 2016, we were able to share about 1.2 million anonymized OCT scans with them in an effort to develop a deep learning system for sight-threatening macular disease. So essentially, to run on these three-dimensional OCT volume scans to identify people with sight-threatening disease and to see how we could prioritize those people to be seen and treated by an ophthalmologist. Now, that was 2016. We worked really hard with the team from DeepMind, and I have to say it was a brilliant experience to work with them. And that was a team led by a German professor called, who of course is very famous in the field, Olaf Ronneberger, the inventor of the UNet. And so it was such a learning experience for me to be able to hang out with these guys and work with them over the course of multiple years. And so in August 2018, we were able to publish the first results of this work. We published in Nature Medicine. And then, of course, this being AI, you can't escape the hype around it. And so it was very nice to see that we got global media attention. Before this in my career, I published loads of papers, and I put my heart and my soul into these papers, and they're probably read by like 10 people. And so it's nice to get that type of attention, but also kind of awkward. Because the fact of the matter is, this is August 2018, and you're getting the tube in London back home, and you're seeing people reading this type of headline, and what you know is that you haven't saved the sight of anyone yet. And in fact, fast forward to 2024, the AI system we've developed is still not being used in the real world yet. And I'll tell you a bit more about why that is shortly. So before I do, let me just show you the algorithm in action. So, I mean, this was pretty cool back in 2017, 2018. I guess it seems like prehistoric now when we look back to those times, but essentially we had two neural networks. The first network is a segmentation network, and we've trained that to segment between 10 and 15 different anatomic and pathologic features. And then that feeds into a second neural network, which is a classification network. And you can see on the top left that it's saying a referral suggestion. So it's saying urgent referral, and then it gives a diagnosis probability. And so it does a multi-class classification. In this case, it's saying choroidal neovascularization, or CNV, 99.5%, and recommending urgent referral. And so we deliberately constructed in this way because we wanted to have some kind of element of interpretability. We wanted it to be able to be more easily transferable between different devices. And because it was also nice that it could provide all these quantitative metrics about subretinal fluid and intraretinal fluid and all of these things that are interesting to ophthalmologists. Now, the other thing that I want to highlight about this collaboration with DeepMind is that this was potentially controversial because this involved collaborating between the National Health Service in the UK and a company, and with industry, and not just any company, but a company whose parent company is a multinational tech company like Google. And so we're very proud of the fact that we took a lot of time thinking about information governance and data protection and patient and public involvement and ethical approvals and just doing things right. And so, in fact, it was very nice then. In August of 2022, there was an article in the Telegraph newspaper in the UK And it was talking about some other work that we weren't involved with, and Google being sued. And this is completely separate, and I don't know what the rights and wrongs of this particular case. But what was exciting for us is that when we read this article, the last paragraph of this article, there was an interview with this guy called Phil Booth, who's an expert in medical data and patient privacy. And so he said that it's perfectly possible to carry out open, ethical, responsible science and health research that has real benefits, such as when Moorfields partnered with DeepMind. And so for us, that was a real vindication of what we had done. Now, where are we now in 2023 and 2024 with this work? Well, let me tell you about a little anecdote about a guy called Ken Cukier. Ken is a senior editor at The Economist, and he's the person who wrote the book Big Data that, a decade or so ago kind of got everybody excited about the potential of huge data sets. And he had written about our work, and he was aware of our work in The Economist. And so back in 2021, he developed loss of vision in one of his eyes, and it was on a weekend, and it was in the middle of a lockdown during the pandemic. So he sent me an email saying, like, what should I do? And so I gave him a call, and I was able to talk him through where to go into Moorfields, to come into our emergency department to get seen and get treated. And so I found out afterwards that when he went into the emergency department, he was checking in with the receptionists and having his vision checked with the nurses and seeing the doctor. And he was asking people, where's the world-leading AI system that I heard so much about and that was on the front of all the newspapers? And the nurses were looking at him like, what are you talking about? And the doctors were looking at him like, what are you talking about? And of course, it's because the AI system is not actually in real world use. And so anyway, he got seen and he got treated. And a few days after he was treated, he put this tweet out where he kind of teased us, praised us and teased us at the same time, where he said, AI is a fraud. I went to Moorfields for emergency eye surgery, and instead of DeepMind's cool algorithms diagnosing young robot surgeons, I had to accept the excellent skill, thoughtful care of human medical staff. What a disappointment. And so, as it happens, the eye condition he has is not something that we would diagnose with an OCT scan. So therefore, the AI system wouldn't have been able to help. But nevertheless, it's an important point that he made, that there's moving beyond the hype of these systems, that this system is not actually out there yet. And so he actually very kindly asked me to come on his podcast, which is called Babbage, to talk about some of these challenges of going from code to clinic. And so just to sort of highlight those, there's multiple challenges. And I think that the obvious ones are clinical validation. So, okay, so you've done a proof of concept in silico on a retrospective data set, but actually, do you need to do prospective clinical trials, multi-center trials? What type of external validation do you need to do? Do you need to do like recurring local validation? Do you need to do randomized trials, et cetera, et cetera? And then the other big challenge is how do you align that with regulatory clearances? And typically, if you have an AI system, if it's going to become a medical product, it has to be built under a quality management system according to ISO certifications. It has to be done with appropriate regulatory expertise, and that can cost millions of dollars and take years of expertise to be able to do, particularly if you're talking about an autonomous AI system. So those are, I think, obvious challenges, but the bigger challenges actually are questions around how do you integrate the system? So how would you take our AI system and integrate it with an ophthalmic imaging system from Zeiss or Topcon or Heidelberg Engineering or one of the big companies? How do you deliver it? And then also, what are the business models for this? Is it a click fee? Is it a subscription? Is it used to sell more hardware? Is it for free? But of course, these things will cost millions to take to regulatory approval, and so the money has to be sustained in some way. And so I used to think that you should always focus on the clinical challenge first. But I've begun to think that maybe we should be thinking about what's a viable business model before we even start to think about the clinical challenges. And then just more broadly, like implementation and adoption. So, if you have an AI system that requires data to go to the cloud, and maybe the inference takes like 1 minute or 2 minutes, in some patient pathways, that's already enough that it's not going to be able to be adopted, because the nurses won't want to wait 2 minutes for the output of the algorithm to come back down to them and allow them to change some action. And so these are all really difficult challenges. And we haven't really solved any of these in most cases with clinical AI systems. And so for me, despite that kind of caution and skepticism, I do think that we are on the cusp of something pretty big. And I think there are parallels with the dawning of the electrical age. And so one of the people that I like to read a lot about is Thomas Edison. And so I think sometimes we're sort of biased to think that all the innovation that has occurred has just been since the 1960s or since the 1980s or the 1990s or just since the internet. But in fact, the 1880s, if it could be argued, was just as innovative in many ways. And so Edison, people commonly talk about September 4th, 1882 as the dawning of the electrical age. And that was when someone from Edison's company flicked a switch and they lit the Pearl Street district of Lower Manhattan. And the key point was that for 20 years before that, there had been lots and lots of inventors who had come up with incandescent light bulbs. And there's over 20 different patents for light bulbs that were a carbon filament in a vacuum that's pretty similar to the patent that Edison got in 1879. But there was two main issues. So the first issue is that those light bulbs, they would work for 2 or 3 minutes and then they would fizzle out. So the inventors would get a journalist to come in and they'd say, look at my amazing light bulb. And then they would just push them out of the room before the journalist could see like that just a few minutes later, they stopped working. So Edison, of course, was able to get something that was longer acting. But actually what people don't realize with Edison was that it was much more than that. And so actually where his genius really lied was realizing that it was about having a reliable source of electricity. It was about having a distribution system. It was about having a connection system. It was about having some sort of measurement system in people's homes as a meter so that you can actually measure how much electricity was being used, and then you could have a business model. And so Edison realized it was a network of innovations that was required. And I feel like we're still in medical AI, we're still in the 1870s, and we don't yet have this network of innovations that really allows these systems to be deployed. Now, the key learnings from the Moorfields DeepMind collaboration, so the first is that we began to develop the infrastructure at Moorfields to aggregate and curate our data. And I'll tell you a little bit more about that in a moment. We learned a hell of a lot about information governance and data protection and how to use routinely collected data and do it in the right way. And then the other thing about it was that our initial work was with industry, but because that work became more prominent, it became much easier for us to develop links with leading academic centers and develop collaborations with computer scientists at UCL and Cambridge and other centers around the UK and internationally. And so that has led to a number of things. So in September 2019, we got funding from the UK government to form something called Insight, which is the health data research hub for eye health. And so this is a national bioresource of ophthalmic data. And so essentially that allowed us to build out our infrastructure and to move it to the cloud. And so in terms of our infrastructure at Moorfields, we have a cloud-based infrastructure. We have more than 20 million ophthalmic images. Here's a typical dashboard that we have where you can see, and this dashboard, it's a little bit old now, but it's got more than 18 million images. And we can generate anonymized data sets with very detailed clinical metadata and make those available in Google storage buckets to researchers affiliated with our group, who can then take advantage of GPUs in the cloud to train the models and so on. It was only because of that infrastructure that we're able to train the foundation models that I'll tell you about shortly. The other cool thing is that we've started to, so this is an updating data pipeline, so it updates on a nightly basis. But the other cool thing is that we're running a number of models. So the model that we developed with DeepMind, which internally we call Octane, that has run in the top right there on over 2 million historical OCT scans, and it runs automatically on every new compliant OCT. And then the segmentation masks and the tissue volumes and the softmaxes all go into our database to enrich the quality of our data. But we've got other models. So this is a model called Automorph that does automated image quality assessment and derives retinal vascular metrics like tortuosity and caliber and fractal dimension, and again adds all of that information into our database. So we're continuously trying to enrich our data. Now, the other thing to say is we think we've built the world's largest ophthalmic imaging bioresource. So we're also proud that we've really tried to set a high standard in terms of governance. And so we have an independent data trust advisory board that gives us advice and oversees all of the work we do. Now, that we've also had another program of work, something that we call oculomics. And this is the idea that we can use the eye as a window to the rest of the body. Of course, we've known for more than 100 years that you can see signs of systemic disease by looking at the eye. Now, what's happened really is since 2018, we've realized that with deep learning, you can unpick a lot more information from these eye scans, these high dimensional images. So we know, for example, with deep learning, you can look at a retinal photograph and you can say whether it's a man or a woman. And with deep learning, you can give a pretty good estimate of the patient's age. You can say whether they smoke or not, whether they're diabetic. You can even give a pretty good measure of their blood pressure and their body mass index. And you may say, well, what's the point? There are easier ways to tell if it's a man or a woman than applying deep learning to a retinal photograph, or there are more accurate ways to measure blood pressure than estimating it from a retinal photograph. But of course, the reason why ophthalmologists got excited about this is because actually it's not something that we know how to do. So I've been looking at retinal photographs obsessively for more than 20 years, and I can't begin to tell whether it's a man or a woman looking at the retinal photograph. And so it suggests that there's a lot of biologically significant information that's locked within the high dimensional data that we can maybe just begin to unpick if we can just get the right data and the right labels and so on. Now, with this in mind, we created something called the ALSI study. And so this was facilitated by all of the learnings about data protection. So essentially, this is a study on patients aged above 40 years at Moorfields who had imaging done over a 10-year period. And we got permission to link the images to a national database in the UK called Hospital Episode Statistics, or HES. And this is a database of every inpatient admission, outpatient admission, and emergency department attendance. So if you have an eye scan at Moorfields and then you move to a different part of the country and you have a heart attack, or move to a different part of the country and have a stroke or any systemic disease, then we have that linkage. And so we reported our cohort profile in the BMJ Open in 2022. It took us 4 years to get permission to make this linkage. And I just highlight some of the initial numbers here. So we had about 350,000 patients, 1.3 million linked hospital admissions, and about 6.3 million eye scans in the first tranche of data. And so in terms of systemic disease, we have about 10,000 incident cases of ischemic stroke. And we know that by comparison, in studies such as UK Biobank, we only have about 700 incident cases with retinal imaging. We have about 12,000 cases of heart attack, versus about 1,000 in UK Biobank, and about 13,000 cases of dementia versus about 250 in UK Biobank. And so we have been focusing really in the last year or so on processing and analyzing data, beginning first with our TopCon data. And so we've been essentially exporting all of these images and then processing the images, cropping them, converting them to right file formats, etc., segmenting them, and beginning to do experiments. And it's really only been possible for us to do this at such scale because of this kind of cloud-based infrastructure that we have. Now, just to highlight funding-wise, UK Biobank is about 250 million in funding, and the Alzheimer's study was funded by a grant for £15,000 from Fight for Sight and Alzheimer's Research UK. And so I call it Biobank on a shoestring, because remember, it's taking advantage of data that's already collected routinely in the National Health Service. But the challenge is just getting the appropriate permissions to be able to use that data in an ethical and compliant way. So some initial results, well, we published a paper last year where we showed changes in the retina in patients with schizophrenia. And then in August of last year, we published a paper in Neurology where we looked at changes in patients with Parkinson's disease. And so the key thing was that we had about 700 cases of patients with Parkinson's disease in Alzheimer's. But then one of the things that we like to do is see how we can combine our data set with other data sets such as UK Biobank and take advantages of the strengths of UK Biobank versus the weaknesses of our data set. And so we were able to look at about 50 incident cases of Parkinson's disease, and we were able to show subtle changes in the inner retina in these patients. And then the exciting thing was that we showed changes on average about 7 years before the patients were actually diagnosed with Parkinson's disease. So we think that this field of oculomics could be a game changer with huge public health implications. And so part of the reason that we think that is because we know that about 9% of patients will, between the age of 40 and 60, go and have their NHS cardiovascular health check. But we know that in a similar age range, about 80% will go and have an eye test. So what if we could pick up some systemic diseases by an eye exam? That could have huge public health implications. So the last thing I want to talk to you about is how we've leveraged all of that to build foundation models. And so the exciting thing, I think, for everybody in this audience and everybody in the field of machine learning has been the fact that there's been such progress. The progress seems to be accelerating just in the last 1 or 2 years, such that when we think back to 2018, it feels almost like a different era in deep learning and machine learning. And so The Economist wrote about this in July 2022. They had a cover story. They talked about how huge foundation models are turbocharging AI's progress. And of course, probably everybody on this call knows about the preprint from a group led from Stanford about where this term foundation models was coined. And of course, foundation models is a term that's a kind of a rebranding of a concept that's been known about for decades, that of kind of pre-training or transfer learning to a large extent. And probably as most people on this call know, really what's advanced this has been the advent of the transformer architecture and the advent of new approaches to self-supervised learning. So we're starting to see, of course, huge attention being paid to large language models in all aspects of healthcare, in ophthalmology, probably like all other medical specialties. We've seen, people evaluating, can ChatGPT answer the board questions? And a member of my team called Faris and Taki was one of the first people to write about this in ophthalmology. And again, it was exciting that just from the beginning of 2023 to the end of 2023, we saw the big jumps in performance going from like GPT 3.5 to GPT 4, and then similar amazing jumps in performance from the other, LLMs from Google and the other open source LLMs, of course, also. And what I've been interested in particular, is vision language models. And so the team from Google have been doing some good work. There's a preprint that I highly recommend people looking at if they haven't seen, where they essentially get a kind of joint embedding of vision and language data, and then they graft it onto a frozen LLM, and then they show it can do lots of really cool stuff. And so, for example, it can do good examples of semantic search, show me examples of a central venous catheter, show me examples of left-sided pneumonia, can do visual question answering, is pulmonary edema present in this image? It can do quality assurance and lots of cool things. And we're starting to see these vision language models becoming available in areas like pathology and other areas of medicine. So where our work comes in and is that we've created a vision model, which is called RedFound. This is a model which is really the brainchild of a guy called Yukun Zhou. And Yukun is a computer scientist who's just finished his PhD with me and Danny Alexander at the Center for Medical Image Computing at University College London. And essentially, RedFound stands for Retinal Foundation. And so we got about 1.6 million unlabeled retinal images. And we were essentially able to train this model and then fine-tune it for 10 or more different downstream clinical tasks, like diabetic retinopathy classification or predicting AMD progression, but also for novel tasks, like predicting Parkinson's or predicting a stroke from your eye exams. Now, the approach for this was using a masked autoencoder, as described by Facebook AI in 2021. And so for me, as a non-computer scientist, it's pretty amazing that you can mask 80% of a retinal photograph, and then the model, you know, given enough examples, becomes pretty good at reconstructing the images. And so here's an example with an OCT scan in the bottom row that I think you would be hard-pressed as an ophthalmologist to reconstruct the scan in the way that the model does. Now, we trained this using a vision transformer architecture with 300 million parameters. It's a relatively small scale compared to these large language models that we're seeing with commercial AI labs. And then we show that it performs very well, is robust, etc. But then we did quite a few experiments where we looked at things like fairness. And so, for an example, with an exemplar task of predicting heart failure from a color fundus photograph, we saw that the performance is maintained in different populations, different ethnic populations within the cohort. We also show that it's more label efficient. And so again, looking at heart failure prediction on color fundus photographs, we see in red that RedFound has better performance than other comparator models, and that performance is maintained even with 10% of the training data. So in September 2023, it was exciting that was published in Nature. And then one of the cool things I think about this is that we've made this open source, and so we've made both the model code and the weights open source. And so we hope that other people can use this as a cornerstone. And we're already seeing papers that are coming out that potentially have better performance than what we've described, and they're building on the work that we have done. Now, so just to finish up then, in the next steps for this model. So we've trained this on 1.6 million images, but actually we have more than 20 million images in our pipeline. And so we want to scale this up. We want to go from 2 million to 20 million. We want to greatly increase the model size and complexity, and maybe some interesting things will happen. Although maybe 20 million is not sufficient to start to see things like emergent capabilities. We're also adding language. So we have about 6.75 million doctors' letters in our system, which contain free text. And so we're in the process of adding those, and those are paired to patient visits. And so we want to see if we can create some vision language models. We're trying to make properly multimodal image models in the first instance. And then we've also trained a 3D version of RedFound, which is computationally quite challenging. But we think that that's going to be necessary to get the best performance from OCT, which of course is a three-dimensional modality. And then we're also exploring federated learning, because the fact is, I think that foundation models will significantly change practices around collection of large medical data sets. I think increasingly we're going to see healthcare systems moving towards the cloud in the same way that a lot of our personal lives have moved towards the cloud. And I think that, combined with privacy enhancing technologies such as federated learning, will help with this. And so I'm working with a startup called Bitfound, founded by a guy called Blaise Thompson. And Blaise was the chief architect for Siri at Apple. And members of the team from Bitfound created the federated learning system that Apple uses on their iPhones. So I've been working with them. You may see me hiding at the back right of this picture to see how we can begin to develop and train foundation models using federated learning. So this is my last slide. I think I've probably talked for way too long. I hope that I've begun to give you a sense that we're working really hard to take technology such as the slit lamp biomicroscope, which is more than 100 years old, and really see how we can reinvent it for the 21st century using artificial intelligence. And then, as promised, that's my email address. Please do get in touch. Thank you very much.